Hello, everybody. Welcome to Geospatial Talk. My name is Eugene Cheipesh. I work at Azavea. We're located in Philadelphia, and we have a mission to advance geospatial technology and apply it for positive social and civic impact. One of the ways that we do that, well, both of those things, is by contributing to a project called GeoTrellis. It's an open source library written in Scala for distributed geospatial processing, obviously on Spark. We get the batch and the stream by that virtue, and we also mostly use it to write web applications, batch jobs. We were here a couple years ago talking about using spatial-temporal indices to store large raster datasets on Accumulo at the time. We've extended our support to these things. It's kind of no longer the interesting part of what we do. We've spent some time recently implementing and distributing more interesting operations like these. We'll talk about one of them in this talk. And also extending the types of data that we work with. My particular favorite there is vector tiles, this idea of quantizing a geometry and cutting up into tiles along with some efficiently packed metadata. Generally, this gets used to display and style tiles on smartphones and web apps, but there's interesting applications of that for analytics. But what we haven't done until now is really focus on the interactive and data science aspect of what we're doing. And try as I might to convince people that Scala workbooks are a totally awesome way to do that. They just don't seem to agree. Something about generics and implicits scares them off. So this project, Geopyspark, is our attempt to take the core workflows from GeoTrellis, bring them into a Python workbook, and kind of try to reinvent as few wheels as possible along the way. We want to expose our raster tiles as NumPy arrays and try to do as good as we can on the actual serialization and transfer between JVM and Python. So we're going to drive it around a little bit with a little bit of code, a little bit of pictures, a little bit of maps, and we need a scenario. Kind of to keep us on track, the scenario is we have some bad apples that came into port. We have a limited time window to figure out where they could have gotten to. We could kind of draw just the radius around the port. That, however, has nothing to do with the geography of the place. So what we really want is a cost distance model, something that accounts for where we start from and how we can traverse the terrain around us to get where we want. You can imagine a raster, kind of like a grid of cells over a map, as a graph where each pixel has 8 neighbors. And for instance, starting in the lower left corner, taking the greediest path along the way, we're going to end up in the upper right corner. And if you imagine those values are time that it would have taken us to traverse that space, we can add them up and actually see the value of how long it would have taken us at the minimum to get to a particular place on a map. So if you repeat this for every possible path, take the minimum, that's what we're going to end up doing. So what do we have to consider in order for this to be geographic in any way? We have to look at our roads. We have to look at the terrain, what is covered there. And we have to look at the slope of the terrain. So we're going to need to bring a couple of data sets together. And we'll start with probably the most interesting one is OpenStreetMap. I'm going to try to get a road network out of it. It's a pretty amazing data set. It's kind of hard to believe that it's free. Aside from roads, buildings, parks, waterways, it has a bunch of annotations as well. The editor kind of gives you the idea of what it is. It's community built. And if you're, in general, thinking about doing machine learning on geospatial, perhaps satellite data, you're kind of immediately thinking like, hey, that's my labeled set. So this is very appealing. But if you go to try to use it, what we kind of find out right away is that underlying is the relational model. We have a notion of points and labels attached to them, how those points are stringed together, and then those strings aggregated themselves into larger geospatial semantic objects like boundaries or administrative regions. In reality, this lives in a Postgres database, and it does its job wonderful, but no good for us, no good for distribution. The really good news about that is, as of last year, the full data set, including the history, the latest, well, I'm not sure if they're publishing the change that as well in this format, but possibly. But nevertheless, the history and the latest are published in the org format, the evil twin to the Parquet file that has received much love in Spark 2.3. And we can grab it directly from AWS, taking a look at the schema. I'm just going to puzzle here for a second, see what we see. We infer, and I'll tell you that this is an immutable data set. As things change, the versions of the records increase. As things are deleted, they become invisible. There is the tag map up to the front, which contains a bunch of metadata. So to make this useful, we will need the geometries, and we'll need something to work with. So yeah, that's Geopyspark. We're going to set up the place that we will save our products and actually grab the org. So Spark memory turns out is a pretty good place to join a bunch of records and reconstruct the geometries, which is what's happening over here. The interesting thing is that once we're done, in the spirit of interrupting with the Python ecosystem, we get a shapely geometry and then just a map of things associated with it. So there, it happens to be a highway. It's a crossing, I guess a zebra crossing. That's pretty cool. We can work with that. Since we have a PyRDD with a map, we can just go ahead and filter it, separating that into paths and roads. The reason we do that is because we need to assign kind of the speed at which a particular road can be traversed. For a path, we're going to go with 3.7 kilometers per hour, and for a highway, we off-screen defined a function that parses the key value map associated with the geometry and extracted the appropriate speed, kind of taking care to clean up the metadata. Since this is a public data set, it's not perfectly curated, but it is pretty good. Well, now that we've got that thing in memory, we're going to rasterize it. This is the process of taking the geometries, intersecting them with a raster grid, and encoding the values associated with them. The reason we're going to do it is because we're going to relate them to some other raster datasets. How does that look like in Geopyspark? Pretty easy. And the thing to pause here is to consider the parameters that we're providing. So we're going to specify the projection system that we want. This is the mapping between the round planet and the flat map. JS people spend a fair amount of time making sure that it's the correct choice, so this is something that we have to consider throughout. We have to have some notion of the resolution and some sort of tagging for the no data value. Also, the last parameter actually is the cell size. The raster datasets, they do get large since they're essentially pictures that cover potentially large detail. So a choice between 16 bytes and 8 bytes is potentially gigabytes. All right, so now that we have an actual raster out of the geometries, we're going to do a primitive operation. This is one of the things that we expose as a common building block in Geopyspark, which is a tile to a layout. In general, it's a notion of taking an arbitrary set of rasters or pictures and imposing a grid at a particular resolution over that. In this particular case, we are imposing the global grid, something that covers the world, in the projection of Web Mercator. That's the EPHD 3857, because we're going to make a web map out of it. In order to do the web map, however, we also have to go through the pyramiding process to get the levels of detail. That's the best I could do with the picture there. But it's a function with only one parameter. We basically give it the partitioner, that's the geohash partitioner, that helps the shuffle along the way. It's one of the places where kind of the reality of working on Spark and having to think about partition counts and partitioning strategies has a large impact, and you have to expose that, and it breaks the nice picture of thinking that you're still just programming a Python process. But off we go. All right, so how do we save these things? This is kind of the bread and butter. We grab the histogram along the way, and we write it out. The thing that is not obvious here, but is cool, is that the layer URI that we're providing to the write function at the bottom is going to contain a schema, and depending upon whether that's S3, HDFS, Accumulo, Cassandra, or whatnot, we're going to load up the correct backend and dump the data in there. All right, so now what can we do with that? We can make a tile server directly on the Spark driver and view the layer that we just saved. And it kind of looks like this. The resolution at zoom level 13 is not the best, but we see the road network, we see the major roads, the minor roads, the paths in the forests, the purple. So this looks about correct. Let's move on to the second part of the puzzle, talking about the walking friction. So we just basically figured out how fast we can move along the roads. What about walking? One thing that we're going to consider first is the type of land cover. We're going to have to grab the national land cover dataset for this. Basically classifies the continental US according to these classes. Water is probably going to be pretty hard to pass, forests harder, urban development easy. So we want to reclassify this into some sort of fraction. First, reading it, because the NLCD dataset is a GeoTIFF, a very common format for raster data. We have a native reader. All we have to do is point it to a URI, tell it how we want to chunk it, and we'll break out the underlying data into those windows, which we then, again, can tile and save out. And apply the reclassification. So that's the interface at the top. We have a Python map that maps from a value to a ratio. We apply it to the raster layer. And that's kind of like the abstraction that we have in GeoPyspark is the tiled in LCD is the tiled raster layer. Underneath, it's RDD of raster tiles keyed by their column and row in a particular layout. So we can save it. We can verify by throwing it into a web map that, yes, it looks good, and continue on our merry way to get some elevation data. SRTM is a global data set that gives us that, and it's wonderful. However, we're going to run into a problem pretty quickly. Well, not a problem first, but so SRTM is provided to you in 1 by 1 degrees of longitude and latitude. This is what the cover looks like over the United States. The problem that we'll run into is that it's its own format and it's not GeoTIFF, sadly. So what Python developers do, and JS people in general, when they reach this point, they say, oh, that's okay, GDAL must surely support it. And in fact, it does. So we're going to use the Python wrapper of GDAL rasteria to try to read it. So what does that look like in our workbook? So picking under the covers, we're going to try to do the same thing. We're going to try to use the rasteria to read out the windows, which is what we want. The thing that we're providing here is the encoding of this read operation into a type that's native to GeoPyspark. We have the spatial extent, the projection, and the raster as the NumPy array. The only thing that we need to bootstrap is figure out where these rasters live. In this case, we're going to write some dirty body code. I'm not sure why this is not in the library yet. The version is 0.4, so I'm guessing it's going to end up there pretty soon. because all we need was to list some URIs and then have a way of filtering them. So another thing that we'll have to do is read the shapefile. We could have done it through Fiona, but in this case, we're going to do it through GeoPyspark, get the continental bounds, and apply them. So these series of slides are pretty ugly, right? We had to lean pretty hard on a couple of functions that we wrote. We brought in some libraries that we had nothing to do with. But the payoff is that that's kind of the interrupt, right? And once you do that, we're able to read the URIs in a parallel manner. And we have this cape hatch to go from a Python RDD of NumPy arrays into GeoPyspark raster layer, which will bring it back into the workflow and allow us to co-register this with other layers and be on our merry way. Coincidentally, if there's an operation we did not want, or rather we did not have implemented yet, dumping the layer into a NumPy RDD and performing the operation there as a Python Lambda is a more expensive but a completely viable way forward. So, verifying the fruits of our labor, we do get an elevation data set. And it gets kind of trippy as you zoom in around Pennsylvania and you see the mountains there. All right, so it's pretty close to time to baking the cake. We have the elevation. We need to figure out how fast we can walk over this terrain. There is a function that does this. In order to apply this function, we need to translate from units of map, which is longitude and latitude, to units of distance, which is meters. A z-factor is something that does that. We apply it to derive the slope. We do another transformation to apply the tubular. And then in the second cell, we multiply the two distributed raster layers with the weights from the land cover. So this is, I think, where it gets compelling. There is, behind these things, a fair amount of shuffling and registering the rasters together, which would be a pain to do if you just sat down and said, I'm going to write a PySpark way to do it. And it's not a lot of fun as having written that myself. All right, so tiling this friction layer and visualizing that, we can look at Mount Shasta, just north of here, and see the effects of our labor. We see the road network that overlaps the terrain. Well, what looks like a hill-shaded terrain, but in fact is related to that. It's how difficult it would be to traverse the mountains. All right, so now we can finally do the thing that we wanted to do. We can apply the cost-distance operation to our layers. That looks pretty straightforward. We are going to drop a point in Philadelphia, probably came up the Delaware. We're going to transfer the friction layer into units of time and pick an arbitrary cutoff point. And after some computation, we get a map like this. I say some computation because in a distributed sense, the cost distance is an iterative algorithm. You essentially never really know whether or not there is a shorter path that goes a roundabout way, and you have to keep iterating until you've reached a state where nothing changes. So we can use this to figure out our answer. In a real analysis, we would probably intersect it with areas for known forests, maybe filter it by elevation. But kind of the hard part here is done. And we can see the effects of the data sets that we used here, where at the edges. All right, so what did we do? Probably the most interesting is using the OpenStreetMap directly from the tap, co-registering the raster layers together and performing an interesting operation on them, seeing them on a map. That's pretty cool. What would you have to do to get this in the Databricks notebook? It's surprisingly easy. You can grab the artifacts from PyPy and the jar from our distribution, load them in as assets, and they'll get attached to your cluster. You'll have to obviously load things like GDAL and Shapely or whatever other Python libraries you want separately, but you're probably already doing that if this is the thing that you're interested in. Where does this go from here? It's an interesting question. So the biggest problem is the serialization, especially when you go to the NumPy RDDs. It's modeled on PySpark, so the communication happens over the Py4j gateway, and Apache Arrow is a potential way to bypass that and something that we'll investigate. We'll implement it, honestly. So the other thing that is compelling is figuring out how to connect these workflows to data frames. In this case, collaboration with raster frames is an excellent way to do it. They expose the tile UDT that enables you to have raster tiles in in Spark data frame, which links it to MLlib. Another interrupt that makes a lot of sense is doing the same thing, but for the JTS geometries. This would give us the interrupt with distributed store like GeoMesa. Provides its results in a data frame with JTS encoded geometries. And that's the thank you slide. Those are the projects I mentioned. The workbook where the snippets came from is at the bottom. And there is a deployment which will package up all the required artifacts for the deployment on EMR with the Jupyter Hub. I will take questions, please.
Can you perform geospatial operations on the Spark raster database?
Yes. So the question is, can you perform geospatial operations on Spark data frame, the raster frame project? Yeah, so it wraps GeoTrellis operations. So as of right now, it supports all the local operations like add, stats, and so forth. It does not fully support the focal operations yet for the reason that it needs to grab the border of the neighboring tile. But that's the support that's going to be coming in the near future. It's basically the next logical step. Have I looked at other? SRTM is the elevation model that we used for, well, actually most commonly. The question is, have we looked at other digital elevation models? We've used NED, which is a National Elevation Dataset, which is easier because it's also in a GeoTIFF format. We haven't used others, but the same process would apply to them as well. Please.
This may be in regards to the OSM data set.
Mm-hmm.
In North America, the coverage is pretty wide. Do you know if basically you have the same amount of detailed assets in other countries, like in Africa and things of that sort? So you can try and replicate this sort of analysis.
Mm-hmm. So the question is the OSM coverage, which is very good in North America, as good in other countries? So I can specifically tell you that it's not as good in Africa. We recently did a project where we compared the population density raster from WorldPop with the building density raster generated from OSM to identify areas where there is a mismatch. And there is quite a few. It's pretty common, for instance, in Botswana to find pretty large cities that are very starkly half mapped or not mapped at all. But Obviously, the situation gets better in other places.
Are you planning to support map matching in the future to OSM?
Am I planning to support map matching?
Yeah.
I'm not sure what that is.
Like having GPS points connect to OSM network using the library?
So that's an interesting question. The question is, can we use the GPS points to connect to the map? So essentially a way to query OSM.
Yeah.
So the thing that we're doing is we're reconstructing geometry and putting them in Spark memory, the thing that would usually be done inside Postgres. What you do with them after that is kind of up to you. We're not looking to make them queryable. The thing that we're doing with OSM once we reconstituted the geometries is we're baking global vector tile layers and querying those. So that would be one way to achieve that, reconciling a query to a particular vector tile and reading the geometry out of there.
So you mentioned the cost distance modeling.
Mm-hmm.
It seems like you're focusing on walking. Are there similar applications in the sectors where you can have basically apply the same model for vehicles or there's certain models?
Yeah, so the question is, we focused on walking. Other applications for this for vehicles. Yeah, in fact, so this does, in a primitive way, consider the vehicles as well. Something I didn't point out, but we did, is on the last line, we combined the walking friction surface with the OSM friction surface. And if you remember, the OSM friction surface would be in basically road speeds. So this potentially, I'm guessing the question is for something like a delivery network, like how far can you reach from a particular distribution center? So with some tuning, this would essentially answer exactly that question.
Has there been any work in the direction of tying GeoTrellis into or Spark streaming API to be able to support not just kind of a one-time generation of tiling, but hey, I've got new real-time data coming in, I want to regenerate some of these tiles as we go.
So the question is, what about Spark streaming? Has GeoTrellis done anything like that? So not publicly, but we have specifically with GeoTrellis, not Geopyspark. We have built Spark streaming applications which will consume a Kafka stream of latest satellite imagery, process that, and generate direct products, throw them where they need to go. So the story there is that Spark streaming does a pretty good job of reusing the RDD API, and you just have to consider the streaming plumbing on top of that, and you're more or less good to go. All right. Thank you very much.